So hello, good morning, and welcome to this session about network performance, where we are going to have three speakers that are going to share with us their experience and their work on networking performance to improve the network performance. So we have a change within the program because our first speaker has some delay, and we are going to change for the second one. And I hope that Richard is going to come at some point during this session. So let me introduce our first speaker. Is just a moment, Brecht Vermeulen, yeah, more or less, who is working at the Ghent University in Belgium. So can you start?
Okay, thank you. So, good morning. Thanks for attending this session. It's not that many people, but it's one of the last sessions. So I will tell something about ideas of bandwidth on demand for using in media production for broadcasters. So the idea of a broadcaster workflow is as follows. So people coming in from doing camera work in the field, so they have raw video material. The raw video material should be produced in a kind of media production, so it should be cut, it should be edited and so on, and then it finally goes to a play out. After the play out or during the production, there is also kind of archiving, so for future needs, so material may be archived. So this is the simplified workflow we envision. So a little history about workflows in the media world. So in the first step, they had linear editing. So the idea was so digital tape. So the video was already a long time digital, stored on tape, and with linear editing. So they had different video recorders. They put in the multiple tapes, and then they took the parts they needed from each tape and stored it on a third tape. So this is what you see here. It's stored on a third tape. Then some more editing can be done, some voiceover can be recorded on another station. And finally, the tape is played out to the broadcast thing. So this is linear editing. So now they are evolving to non-linear editing, and the idea is to have, the files or the video is still stored on tape in a digital way, but now it is, with such a video recorder, it's ingested to a computer system, it's converted to a file, and then the file is edited and edited in a rough cut, in a final editing, voiceover is added, but these are all different stations. So in some steps it can be written back to tape again, and then finally it's played out. So the editing is non-linear here, so it's much easier, it's based on computer systems, as you know it, and this is the phase where most of the broadcasters are now certainly in Europe. And one of the next steps is to evolve to digital files. So we had digital video on tape, but now they are evolving to digital files. So the idea here is, so you have here the tape coming from a camera. It is ingested to a central storage system as a file, and then all the editors work on that central storage. The playout is done from that central storage, and it is also archived from that central storage. So this is the future, and the broadcasters in Europe are evolving to this kind of workflow. Besides the digital tapes, there are also cameras with memory devices or Blu-ray discs, and there it is stored already as a file. So this is kind of new cameras. For the nonlinear editing clients, most are Windows or Apple-based for that. So files, what does that mean? with standard definition, you have typically 25 megabits per second or 50 megabits per second as a video stream. So this means for 1 hour of video, you have 13 gigabytes. Transport over gigabit network is, almost 2 minutes. It's acceptable. However, if we look at the high definition case, the files grow a lot more. So for instance, the HDCAM SR codec is 440 megabits per second. So this is, files of 200 gigabytes for 1 hour, which is certainly very large. So which are the research issues for this? So we want to look for the optimal large file transfer. So what is especially the network and the server performance? How can we tune that? The idea is for high definition editing, that the editors work on the standard definition files, and then offsite it could be transcoded or rendered to high definition. So it's the application of media grids where farms are just computing in a remote site, and the files have to be transferred to there. So also for file-based archiving, how can we transport the files to an archive in an optimal way? Also disaster recovery. So if you have that central storage where the people are working on, if that crashes, you want to restore that files that they can work on or provide alternatives for that. So first we looked in the TCP tuning options. So there are some things which are possible for free. So you can tune parameters, for instance, in Linux and Windows. Of course, the receive window, which makes that more data that can be in transit. And well, there you see the Linux and Windows parameters which we have tuned, and which make that you can reach 1 gigabit really on such a network. Other things we considered are jumbo frames. So jumbo frames can cost a little as not all devices support it. It's also not really standard, so it has to be tested before. For instance, some NICs do not support it. Some switches maybe also not, so you have to test that. I guess. So other things are the TCP checksum and segmentation offload. So it's supported on most modern network cards with a standard kernel, but some cards do say that they support segmentation offload. For instance, in Linux, you can see it through ETH tool that it is supported, but in fact it's done by the driver in software. So the driver says it is supported, but they just do it in software. And then we also have the full TCP offload cards, which we have evaluated. So the complete TCP IP stack is done on the NIC. So including retransmit, slow start, and so on. However, the TCP setup and tear down is still done on the server or the host. So this means, for instance, for a web server where you have a lot of very short connections, that an offloading card is not really a good option. There are also problems with, for instance, bundling. So bundling different interfaces for failover or for double performance. And you need a kernel patch for it. So here you see the difference between the normal network cards on the left and the offloading cards on the right. So the idea is you have two servers with 2 CPUs each and network card. So the flow goes from the CPU, sends the data through the network card over the network through the other CPU, and there it is ACT. So the thing is, if a packet gets lost, that the host CPU has to resend it here again. However, with offloading cards, all that is done on the network card, so the CPU has a lot less to do. So the tests we've done for that, so we've compared the Intel Pro 1000 cards with the Chelsea offloading engines. And both cards are supporting 4 ports of 1 gigabit. And we've done this on a dual Opteron server at 2 gigahertz. So 4 links between the 2 machines. And tests were done with iPerf, so you have memory-to-memory stream, so it's more or less the upper limit you can reach. Very important for this is PCI bus. So normal PCs have PCI bus of 32 bits, 33 megahertz. This means that only 1 gigabit is possible over that bus. So if you have the full duplex, so the data and the AX coming over that bus, you cannot reach 1 gigabit over the network really. So we used the server buses PCIX at 64-bit, 133 megahertz, and there you have 8 gigabit of maximum capacity. Recent PCI Express is of course better as it is a point-to-point communication over the motherboard. So there you don't have the shared bus principle. The maximum TCP throughput you can reach theoretically with normal MTU frames is 941 megabits per second. And of course, if you increase the MTU to jumbo frames, you reach a more efficient communication. So the results. Here we see on the left the throughput chart. So first for a normal MTU of 1500 bytes, you see that the Intel card, so over the 4 links with 4 unidirectional flows, we almost got 2.7 gigabit per second. With the Chelsea offloading card, we got 3.7, which is the maximum you can reach on 4 links as data throughput. So if you look at the jumbo frames, so 9,000 bytes, you see the Intel does a lot better. The Chelsea, well, it's still the maximum, of course. It doesn't change. If you look, however, at the CPU load, we see that for the Intel cards at 2.7 gigabit per second, you have almost a load of 80% CPU. For the Chelsea, it's only, well, about 40%. If you use on the Intel card jumbo frames, you see a decrease in CPU load, which is really a lot, so it's only 45%. So jumbo frames does matter, of course. For the Chelsea card, it doesn't matter. It's 2 times the same CPU load. If you look at 4 bidirectional flows, so we have here, with the Intel card, we only reach 3.2 gigabits. It's not that lot more than with 4 unidirectional flows. However, with the Chelsea card, we reach up to 7 gigabits per second, which is less than the theoretical maximum. But of course, we had PCI Express, which only could provide 8 gigabits per second, but we have flowing the data in one direction, the AX in the other direction over that PCI bus. So that's more or less the limit for those things. If you look at jumbo frames, so Intel does, well, a little better than with normal frames. The Chelsea is just the same. If you look at the CPU load, so you see with the Intel that the CPU is loaded maximally. So this is the bottleneck. For Chelsea, as said, it's not the CPU which is the bottleneck, but probably the PCI bus in this. So after that iPerf thing where you just compare TCP performance, we've compared also the protocols on top of that. So it's FTP, NFS, and CIFS as, well, the really file transfer protocols. And for this, we had, well, a 4 CPU server connected to a SAN with GPFS fiber channel storage. So measured on that server, we had a maximum write speed of 2.8 gigabits per second and a maximum read speed of 5.5 gigabits per second. To that server, we connected 4 clients, each with 2 gigabit links over an Alcatel OmniSwitch switch. And with those clients, we tried to load that server and see how much throughput we got with all the clients together. So here we see the results for that. So we have the bandwidth in gigabits per second, and we have the three protocols, FTP, NFS, and CIFS. We have read performance and write performance, and for the Intel and the Chelsea. So if you look at read performance for the Intel card, we have something, well, 3.8 gigabits per second. For FTP, NFS is a little less, and CIFS is also less. With the Chelsea, we reach approximately a little more than 5 gigabits per second. So if you look at the performance of our SAN, it was 5.5 gigabit read speed. So here we reached the bottleneck of the SAN with FTP. NFS and CIFS doesn't go that high. With write speed, we see that with the Intel card we got some 2.5 gigabit, which is again the write bottleneck of the SAN. We also reach it with the Chelsea. So here, in the writing, you don't see a lot of difference between Intel and Chelsea offloading card. However, on the read side, you see the differences. So important from this figure is that FTP outperforms NFS and CIFS. And depending on the read or write, CIFS is better or worse than NFS. This is, well, we analyzed the CIFS protocol. So it's a synchronous protocol with a maximum block size of 64 kilobytes. So the problem with synchronous protocols is if the delay increases, you have to wait for the ACK. And it takes time where the performance goes down. So we see this in this chart. So if you increase, for instance, the host delay, or this may also be the network delay, the throughput, which is in megabyte per second in the figure, decreases very fast. So for instance, if you only have 1 millisecond of delay, it's almost, with the highest block size, it's not more than 40 megabytes per second that you can reach. So on our network-based vision, so we first will list up some broadcaster problem, and then 3 typical cases, so the media grid farms, archiving, disaster recovery, and where the problems are, how we see that a network-based vision can well, improve that in the future. So what are the problems of broadcasters? So they work together with different production houses. They have remote studios. So they are spread geographically in doing their business. Storage and computing is not really their core business. So the idea would be logical to put that in data centers to make it doing, to outsource it to other providers and so on. So it seems all very logical, but the problem, as we have seen, is that so we've seen that FTP performs better than NFS and CIFS has that delay issue. So, okay, you can say we skip CIFS, but the problem is that the editing clients, which are Windows-based, are using that as a protocol. So it's not that simple to just say, well, use Linux for editing. It just doesn't exist on Linux. We have also the AGCAM SR, so it's 440 megabits per second, which is a lot. So at 1 gigabit per second, you can also only send it at 2 times the real speed, so it's too slow, really. So the broadcaster also need a lot of storage bandwidth, so both for archiving, so they want to archive their video in a fast way to the archive, and also retrieve files from that. Also, disaster recovery is a real problem. So they are working on a production for the news, for instance, And then if their storage goes down, now the rebuild times are, for instance, 24 hours, which is really too slow. And broadcasters also have the typical time-critical things. For instance, they have the deadlines of the news where they have to make the video available. So media grid farms. So the idea already was to have editing done on standard definition and then do the rendering on rendering farms on HD. So this means you have to render the editing effects, the cuts and so on. So it's logical to put it in a remote grid farm and there let the computation done. The problems we see on that is that it's not really computing intensive task, but more a storage intensive, intensive task. So most grid infrastructure now is directed towards really computing intensive tasks, but here we have little other issue. For broadcasters, there are guarantees needed on the bandwidth and the computing availability. So they have their deadlines. They want to finish their work on a certain time. So the bandwidth to those rendering times should be high, but it can be done by reservation. So for instance, for non-live productions, you could say, well, we will render that from then to then. So I think this is ideally for bandwidth reservations. And that's one of the directions we are thinking of. So regarding archiving, so here we see the disk cost per gigabyte in euros over the last years. So you see, well, a fair drop in price. So this means that online archiving, instead of putting the tapes on a shelf, is really, well, a thing which is feasible and which would be the future. Archiving, so we have cheaper disks, we have cheaper tape library systems. So the broadcasters are now evolving to also store their files online and make them available in a quick way for the future. The storage management is a little other than typical backups, because here we have content which is more important or more popular than others. Some content can be set from the beginning. Well, this is some raw material. We just put it in a deep storage, and we certainly will never need it. But nevertheless, we can put it online. If we put the archives in a network, we can say, well, there's a space component. There's a certain distance or bandwidth to that archive, and we can take it also into account, for instance, to store less popular material on a very distant and cheap location. So the vision we have is that for that video or broadcasting archive, that they will put it distributed over network. So there will be different archive providers distributed over the network, and the broadcasters will just store their content with those archive providers. The problem is, of course, the bandwidth to those archive providers. So the idea here would be that bandwidth reservation for that would be ideally suited. More is that you can do it as not symmetrically, because the uploading of the candidate, so putting it in the archive, can be slow. Doesn't matter that much, but for retrieving video, they want to have it fast. So if they make a news item and they need something from the archive, it has to be there very fast. So disaster recovery was also some item I mentioned. So the idea was, so they are doing production on a central storage system. That central storage system is a couple of terabytes, depending on the size of the broadcaster. And now the problem is if that central storage breaks, they can have backup of most of the material. But the thing is, if you put it back from tape, it takes, for instance, more than 24 hours, and this is not a workable solution. So what are feasible solutions? So maybe we can work on a remote copy. So you have remote copy in another data center. Problem there is the client, which are, for instance, Windows-based, which has that slow access. Networking server performance is, of course, also an issue. But here also, you could work with bandwidth guarantees. Say, well, we have a disaster. Now we want a bandwidth of, for instance, 10 gigabits or more to that certain site, and we will work on that remote copy. So for those items, we're thinking of doing a bandit reservation kind of research. And this is ongoing, but we have now established a VPN connection to the New York University. So it's from Ghent in Belgium through the Belnet NREN network through GR to New York. Well, because they're in New York, they have experience with the Cheetah virtual label switching router. So they have made such a software engine on Linux PC which can drive Ethernet switches for doing bandwidth reservation. So the idea is that we can test with that to see how it can be optimized and if it is suited or not for the broadcaster world. So the conclusions, I've listed some demands from broadcasters. So the bandwidth is certainly a demand for remote storage computing, and they work with very large files, certainly in high definition. So the research we're doing is the optimal configuration and the tuning of the protocol parameters and the servers so that they really can use the available bandwidth, which is not always the case. And then the question is, bandwidth reservation, can it be useful or not? And this is some ongoing research. So I would like to thank you for your attention.
Is there any question to Brett?
Thank you. For your comparison of the transfers with FTP and NFS and CIFS, have you tried to introduce packet loss in the network and then measure the performance?
No, because, well, certainly it will be very much worse than that, but here we're trying to start from ideal networks. So it's a local network, and then we are saying with bandwidth reservation optical circuits, you have very little packet loss.
A very short question. How did you figure out that that it was actually the software driver implementing the offloading and not the TCP hardware card?
For some networking card, you just find it on mailing lists if you look for it. So you can also see it in the driver source code, for instance, that they do it in Linux drivers. So you see ETH2 reporting, well, we support offloading. Then you look into the driver, and they do just the calculations over there. So
you compared the performance of this Intel card and Chelsea card. Are those cards compatible, comparable, so that one is PCI Express and the other is as well, and so on?
So both cards are PCIX. So this is the same. We've just exchanged the cards in the same servers. So we put it in, we compiled another driver into the kernel and did the measurement. Of course, the Intel card is not doing the full TCP offload, so it's a difference in core. But from an application, you don't see the difference.
because our experience with some experiments with Intel was that with PCIe cards, you couldn't get more than 4 gigabits, which seems to be the same that you saw. But I was a bit surprised that with Celsio you get more, but maybe that's because, is it PCI Express or PCIe?
No, we just used, we put it in the same PCI slot.
1 gigabit.
Pardon?
1 gigabit cards.
With 4 ports. Yeah. So of course, if you look at this figure, here the FTP server has 8 ports, so it's two cards, 2 4-port cards. But the IBM server has a particular advantage that they have different PCI buses. So each card is on different PCI bus. So which improves, of course, the performance.
Okay, so thank you. So our next speaker is Richard Hugh Jones, who leads the eScience degree Network Research and Development in the Particle Physics group at Manchester University. So please.
Well, apologies for being slightly late. One day I will master the art of network transport when it's railways. So this is what I would like to talk about, is high performance throughput flows for VLBI, and I'll cover these topics with UDP flows, examining what happens when you try and move constant bit rate data over TCP, and then looking at multi-gigabit flows over GÉANT 2. So, in case you missed Arpad's extremely good talk earlier this week, what is VLBI? Well, you wish to observe some source. You have a signal plane of data, of information coming towards the Earth. This basically looks like noise with a very little bit of signal inside. You receive it by telescopes, and what you receive here is essentially white noise. And you only get the signal out when you take the data and send it to the correlator. This used to be done by tapes, but now what we want to do is send a data wavefront across the network to the correlator. Basically, the resolution you get is proportional to the baseline projected onto the object, and the sensitivity is proportional to the square root of the bandwidth times the time you integrate. So the point is that bandwidth is as important as time, and clearly we can use as many gigabits as we can possibly get. The sensitivity means that we can observe very, very faint objects. So we started to make some tests about streaming data across the network, the European networks, and we started with 5 telescopes, and I always love the pretty pictures of the telescopes. It's much better than looking at particles. Here's the GÉANT 2 network, and we went across the various NRENs to get to Jive. And the idea was to send flows across here and see what effect this had on the network and what effect the network had on the flows. So we developed a simple instrumented program, which we call VLBI UDP for obvious reasons. Basically, we could take data from disk or from memory. This was the input thread. The output thread would chop this into packets, put a sequence number on the packets, send the data to the receiving side. The receiving part would check the sequence numbers and put the data in the correct order in the ring buffer. So it could allow for lost packets. It could allow for packets out of order. Now, you've probably noticed by now that if I lose a packet in UDP, there is data lost. This is one of the few applications that, providing they know they've lost data, they can still do the science. They can correlate the data they have. So if I lose the odd packet, I just have a slightly worse signal-to-noise ratio. Anyway, we tried to get these 5 sites. We ended up with only 3, but we wanted to measure these parameters about the network. So I put this up to remind you that when we try these experiments, not everything goes right every time. And as soon as our pad worked out of the door, we lost a nick. But this is just, we survived. We managed to do a good run. But things don't always work as we would like when we're doing experiments. So what did we find? Well, we actually cheated a little bit. We tried to go from as high rates as we could on different links. So up here is the link going from the UK using a light path. This is from also the UK, the same site, Jodrell Bank, but using the academic internet. And here we were setting the spacing of the packets to 15 microseconds, so you get about 800 megabits. Here it's more like 600. So these look pretty good. Pretty well zero packet loss here, and quite a large amount of packet loss. This is starting to get worrying. And we worked on this with our friendly network site folk, and they were in the middle of transitioning their network on the campus. And so they had bonded 4 1 gigs together. They said, fine, there's plenty of bandwidth for you to play, but they were all half full. So when I tried to put 600 across on one of them, I had a problem. And I also caused problems for other folk. But they were very understanding and didn't throw me out too long. From Bologna, we had, again, excellent throughput, very, very little packet loss, and no reordering. So we think this was a very good demonstration that we can do it. This is now improved, by the way. Well, what effect did we have on the network? Well, quite a lot. This is the access link into SurfNet. And you see, this is our traffic. We ran it overnight, which is why we couldn't repeat things easily, because there weren't people at the remote sites. It's quite a big effect, you might say. Also coming out of SuperJanet and coming out of GAR. So we have to be careful about this, that we don't, if we want to do it like this, not using light paths, that we don't swamp the other traffic. Well, why are we doing it? Well, it's actually driven by science. They really want to be able to make these measurements quickly in real time. And these are 2 examples of the first science call. I think Arpad also showed them. But the point, and they're lovely and pretty, and I think they love, I enjoy looking at these things. But the point is that this was only at 128 megabits a second. But they moved 4 terabytes of raw sample data. It's an enormous amount of data. The other thing they can do is what they call rapid response experiment. And this was a first test to see whether this concept would work. So they operate the 6 telescopes in real time, send the data in real time to the correlator, analyze it, select the sources, and then set up to observe a detailed one source. So this worked extremely well, except unfortunately, none of the microquasars were active at the time, which was a little bit disappointing for the science. So basically, it's a perverse uniform. Okay, so let's move to look at what happens when you move constant bitrate data over TCP. Why do you want to do it? Well, the radio astronomers sample their data at a constant rate at the telescope, and therefore they want to move it. Currently, they are using TCP as the transport because they're a bit frightened of swamping the network. So we set up a test bed of light paths so we wouldn't interfere with anybody, and this is in Jodrell Bank. This is in Manchester, so they join in one VLAN here, go through to Amsterdam where there's a big switch, and these are light paths to different systems at Jive. And what we were able to do was to send data from here to there, from here to there and back again, and you have to be very careful not to join the VLANs or you get a very nasty loop. But we didn't manage to do that. What did we see? Well, in this case, we did induce packet loss. So this is, these are the plots of the parameters that TCP is using, taken from the Web 100 interface. So we've patched the kernel to do this. So these are plots of what TCP thinks TCP is doing, as opposed to what we think TCP is doing. Here you see the congestion window, and this is the amount of data that TCP is allowed to send on the link. This is slow start, nice and stable, and then we drop a packet. Then we go into congestion avoidance, and we slowly recover. This is about 10 seconds here, which is about right, going across Europe. This is the corresponding drop in throughput, and here's the retransmitted packet. what happens to us? Well, if we didn't drop anything, you would get this line. I'm plotting here the arrival time versus the message number. When I drop a packet, there's a delay while TCP retransmits it. It's also dropped down in speed. So all this data here is delayed, and that's what's happening here. The data starts to get later in time of arrival. And eventually, all the buffers overflow, and the telescope will drop out of correlation, and we don't want that.
What's the stat?
Hmm?
What's the stat here?
That's standard TCP, actually. We know. We've got this on others. We can talk later. But this is what most of their systems use. So we're trying to... So is it possible to resynchronize this? Well, this is what I just described. You lose a packet, you get the loss, retransmission, and then this is the delay. So can I do this, essentially? So can I get back to what I expected? And if I can, what are the optimum parameters and what is the pain, as they say? Well, if you can go faster than the link speed, the average speed you're using, you can catch up. So here we have set up the experiment with certain parameters to do that. Here's slow start, here's the packet loss, the drop, and now you see the congestion window opening. So this data here is being sent there. Here is the throughput. This data is going faster now than the average speed. And there's the one packet retransmitted. So what's the price? Well, the TCP buffer to do this is 160 megabytes. You would expect for the delay bandwidth product for this to be of the order of 0.9. So it's very large. You can do it, but there is a penalty. And this is it. That it takes about 2 seconds, 2.5 seconds. So you must buffer that data. So we've concluded that the TCP can be used, but is perhaps not optimal. And by the way, this effect goes as the round trip time to the 4th power. So if you want to go to the States, you need an enormous amount of buffering. Right, let's turn to the second, last topic, which is how can we get high throughput across Géant? Why do we want to do it? Well, I told you that bandwidth gave you a lot of sensitivity, and we would like to couple the telescopes at Onslow to those at Jodrell Bank to test the concept of this. But everybody says, well, fine, good idea, but will it work on a PC? You're wasting your time. Well, we carefully chose the motherboards to be fairly advanced ones, where we have dual core. They have individual front-side buses, so there's no contention here. The memory is serial. We had a memory card in each of these slots, so they're all accessed in parallel. So we're trying to remove the bottlenecks. And we had a couple of PCI 8-lane slots. Into that, we plugged the Miricom NIC, so it's an 8-lane PCI Express card, and we started making some measurements. So this is sending out back-to-back packets, UDP packets, and looking at the round-trip time. Here you're plotting the round-trip time as a function of message size up to jumbo 9K. This is lovely and flat. It should be linear, and the slope of that should be the sum of the inverse transfer rates of everything you go across. We measure this, and if you sum the transfer rates of the various buses we're going across, there's reasonable agreement. You know, you could be picky and say it could be better, but I'm reasonably happy about that. And the histograms of the round-trip measurements are very nice and tight and smooth, with a full width of about 1 to 2 microseconds, which indicates that the PC is really focusing on doing this transfer job and not going off and playing web services or something. What about throughput? So here I'm plotting the received wire rate as a function of the spacing between the frames. So what we do is we send out streams of UDP frames carefully spaced in time, and we measure what happens at the far end. And as you go from here up to there, you are increasing the size of the packet you're sending. So this is like jumbo frames. So the maximum you can get that we observed was about 9.4 gigabits a second. So we were reasonably happy until we noticed that the black line, which is the larger packet, is actually less than a smaller one, which is a bit unusual. So what you should see on here, if it's flat like this, then you've got a limited bandwidth, and that's what you're measuring. This part here should be 1 over t, and it is, because the spacing of the packet is more important than anything else. And the drop here is due to having to set up the transfers, and the transfer time is of the same order as the setup time of the NIC. Also, there's more processing overhead, so that's why this drops down. Okay, we are taking 100% of the CPU to run at line speed, but there are 4 CPUs, and 3 are idle, and if you put jobs into the other 3, they do work and they don't depress this very much. A little bit, but not much. So you can certainly do something useful. Right, what was going on? So we investigated by plotting the wire rate as a function of the user data size, and you would expect this to nicely rise. If you take a simple model here, where the time to transfer the data across the system is some function, constant time plus something times the length, you would expect this nice point here. But you see 2 steps. And if your eyes had been good enough on the first plot I showed you of latency, there were 2 little steps there as well. These correspond, if you do the fits for here, here, and here, to about increasing this by about 0.6 of a microsecond. And we finally stooped to reading the driver code to find out why. And Miricom very nicely tell you that they've done this they deliberately because of some PCIe chipset limitations. So they actually physically chop up your packet, and this is why you get these. There is also a PCIe spec limitation of 4K, and I don't know if the 2 are coincident or not yet. Okay, what about TCP performance on this? Well, we can get up to about 7.7 gigs. Again, it takes most of one CPU, but you've got the 3 others to do something useful. So even with some glitch, which happened because somebody coughed or something, we managed to get, I think, pretty acceptable performance. So yes, okay, it works. So we set up a collaboration with Dante, who operate Géant, and they very kindly allowed us to go into their POPs. And what we wanted to do was test from the VLBI was do these tests, and they were interested in what happens when you get bursty TCP when you've provisioned a lower bandwidth pipe coming out the back. This is work still got to be done, and I'll tell you some results of this now. So the test bed looked like this. I think you've heard in some other presentations that they have an independent test bed which they let us play with. So we didn't mess up anything in the production. And we put 2 PCs in their London POP, and we routed the path through Amsterdam, Germany to Prague, and turned it round and came back again. So this gives us about the length we would like to do. For future work, we're going to change the routing so that we can actually get different lengths and see what the length effect has on the protocols. They were very inventive in using the management tools from Alcatel to actually do this. We first thought that they'd have to set up every element by hand, which would have been somewhat daunting, there being something nearly 200 of them. But it turned out that we could do something much simpler. So our first attempt was to say, okay, I want to go from London to Prague and back. And the wizard said, "You're crazy, I'm not doing it." So what they did is they used the manager to create 2 parallel paths to a virtual node here attached to that interface, attached to the Prague box. That it was more than happy to do, and then all you had to do was manually join the time segments at that point. There's only 28 to do, so he did that very quickly. In fact, we were absolutely delighted when the paths came up. Of course, during this process, there were lots and lots of errors saying, no, you haven't got anything connected and things like that. But they got 28 VC4s connected. The optical length was about 4... oh, you can read the numbers, I've forgotten. But when you put the dispersion compensation in, you get around 46.7 milliseconds. And just to prove we really did go into their POP, here are the PCs. This is the testbed SDH box. This is the production one, which we didn't play with. And this is the optical transport, which carries both the switched IP, the production SDH, and the test HDS. And these little wires here are ours. Right, so what did we see? Well, we saw exactly 4 gigs. So we're very pleased indeed. This worked very nicely. It doesn't matter that this is sending, taking 100%, because we were sending at line speed. We wanted to see what would happen. When you get to about here, which is about 17.5 microseconds, then you're down around 20, 25 maybe, percent kernel mode sending and about 40 receiving. So we think this is quite acceptable. Then we looked at the one-way delays. Now, we can do this, they're relative by, we don't have GPS, but we can do this for short periods of time by synchronizing the clocks at either end in a very simple way. And we found an extremely stable and nice baseline, but were slightly frightened when we saw these spikes that occur every 86 microseconds, and we started wondering, what is it in SDH that can do this? Luckily, we went and looked at what the lab test did back to back, and they're essentially the same. So our conclusion at this point is that the light path is not adding anything that we don't want or don't understand. We looked at the jitter. Okay, this is interesting. You would expect to see a nice sharp spike here. It's pretty nice. But why have we got 2 side peaks? Okay, they're a factor of 100 down. What they usually indicate is that there's cross-traffic and you're queuing on the network. They're about 36 microseconds apart. And it seemed to be independent of the packet separation that we tried. So it's not a sort of loading effect. And again, that's what we saw on the network. And this is what we saw on back-to-back tests. So we need to understand that, but it's not a big problem. And there's certainly, again, no problems with using the light paths. And finally, we thought we'd better see what the stability is like. Well, it's fine to do these little tests, but what happens if we run this for a long time? Well, I think it was the day before yesterday, I ran this for 26 hours, and I think this is pretty stable. This is really very, very nice indeed. We did observe a very, very small amount of packet loss. We shouldn't have any. There's nothing in the way. So we need to understand where this came from. It's so small, it's not going to be a problem to the application, but it's one of those things we'd like to look at. And finally, I would like to thank all the folk who collaborated with us and just point out that Dante really did provide bandwidth on demand, a record 6 hours to do everything, including driving down from their POP, putting the PCs in their racks, connecting them up, and provisioning the light path. Any questions?
So, any questions for Richard? Any question? Okay.
Hi, Richard. On the very, very early slide where you were using the 4 bonded links, there was a time decay effect that things got better over a period. You started off with a lot of packet loss and it dropped off. Is that an artifact of your experiment or of the other traffic that was on the network?
Okay, well, first of all, so those weren't 4 bonded links, by the way. They were 4 independent paths. The effect is in fact due to the load on the campus, this one.
Yes. Yeah.
Okay. This is due to the load on the campus links. Oh, I'm sorry. Those links were bonded. Yes, yes.
Right.
I beg your pardon. I thought you meant these. No, these are independent paths.
Yes.
But that one went down a section where it had 4 bonded links, yes. There was just other traffic on those links.
And so the slope there is the effect of the other traffic
And
change.
as the other traffic died away during the night,
Yep.
this got less.
Okay.
But we were still at the same situation where we were using one link, and depending on who else got onto that link, we would induce loss on theirs and they would induce loss on us. Yeah. Yes, very much. Especially the TCP. We didn't see it on this case, but on another one, we actually saw the TCP into the campus being depressed when we were sending out. So we were really slaughtering them.
One question, you mentioned that those were bonded links. Did you get information how those were bonded actually?
In what way?
Sorry?
You mean, it certainly wasn't round robin with the packet, it was per flow. Is that what you meant?
I mean, was it at the IP level or using, for example, link aggregation control protocol with, on the
this was
Ethernet
level.
level?
This was at the Ethernet level.
Okay.
Because it's adding the microphone for the webcast.
What test equipment did you use to create the flows? Did you use smart bits, just PCs?
No, these were all done by server quality PCs.
Okay.
I mean, basically, we were trying to, in this case, we were trying to test what would happen when they move data and they use real PCs with interfaces into the radio astronomy equipment. So, yes, smart bits would have been interesting to test the network. We were trying to go a little bit further and see what's the effect, include the effects of the end hosts.
Mm-hmm. So, were the packet sizes, did they change? Smaller packets, big packets, or what sort of a stream was it? Was it all the same?
Okay, so these are always the same size packets, and we go as large as we can that will go across the network. So for the 10 gig stuff, it's jumbo. For this, we stayed at 1,500 bytes. I think that's right. Usually says on the slide. Mainly because we didn't want to have problems going through other people's equipment. We can go higher, and it does actually help.
Then one last question, but I might be a bit off here. A rapid TCP or something like that? I seem to remember that existed. Do you know anything more about that? Because you tested TCP and fast TCP, or there's something else?
So,
Yes.
So we didn't test fast because you now have to buy it. We have done a lot of work on different protocol stacks. So, on different TCP versions. They're now all incorporated in the kernel we were using, which is a 2620 with a couple of patches. So these results are all using the standard Reno. Other work we have, which I haven't presented, shows the effect of when you change the parameters of the TCP so that you get, in principle, better recovery. I haven't got those here.
Thank you.
I was wondering if you have any plans to extend your sort of tests beyond the Northern Hemisphere to the radio telescopes in places like Australia, Narrabri and so forth.
Well, we have been talking with the folk from ARNet about their links, and I know there's interest from the science to do this. They're also talking and working with the Chinese folk. So yes, we are very interested to do this. We have already done some tests between here and Chicago because we have test systems there. There are plans to link up with Haystack, again checking out what the network performance looks like. Going to Chicago on our light path, which is 1 gig, we were sending, I think, 3 days without losing a packet, if I remember rightly. This wasn't always the case because there were a lot of problems and the person was looking at them, he was getting several % packet loss or almost nothing. And in fact, we were then getting the travel tickets, so it's very useful to get this information from the travel ticket system, that they were actually having problems with cleaning fibers and replacing cards. They did that and everything worked, and then a lorry went over some cable and broke the fiber, and so we had to try it again. But there are problems like that, and we are very interested to do some work on that.
Okay, so thank you again. Our next speaker is Pekka Savola. He is a network specialist, and he works for the company Scientific Computing in Finland.
Okay. Hello, everyone. I don't take credit for the flashing title. It was from my colleagues from Dante. But the intent of this presentation is to summarize what this function called PERT is, what's the new recent things about it, and look a bit about one performance investigation I was involved with last September to December. Okay, what's PERT? PERT stands for Performance Enhancement Response Team. And the motivation for this function is that the bottlenecks usually used to be in these long-distance links between countries or continents or whatever. And now the capacity has increased a lot, and the bottlenecks may be anywhere. They might be in end system in multiple places there in the application, in the operating system, in the hardware, in the drivers, in the configuration of those drivers. They could be in local area networks, as we saw from the campus weakest link panel yesterday. They could be in the long distance links, and it can be really difficult, especially for those people who are not experienced with debugging these kinds of issues, to find out where the problem is and to fix it. And the concept here is that we will help in investigating and resolving these kinds of problems in performance. And how that's done is that there are we provide some education through deliverables and web pages and so on, where we explain these concepts so that those people who are closer to the technical side can also look at it themselves. We have some measurement infrastructure, for example, these servers where we can do remote measurements and also support. And the philosophy here is similar to what the security side has with CERT. And that's something like 10, 15 years old now, but that has been loosely followed. It seems that the first idea to do something like that actually originated in Internet 2 end-to-end performance initiative. The web pages are still there, but most of the material seems to be from about 5 years old, so, or at least a couple of years old, so I'm not sure what's the status with that currently. what we have in Europe is that in the original GEANT project, there was this trial PERT that included a couple of national research networks. In the GEANT 2, we had this pilot PERT, and now, since a couple of years, we have this production PERT. And how it's organized is that we have this virtual team of about maybe 10 NREN engineers who rotate as a weekly duty case manager who looks at new issues and looks whether any old issues can move forward. And then there are these voluntary subject matter experts from research networks, academia, industry, and so on, who also can provide some input in the mailing list. We have a ticket system. Unfortunately, at least from my perspective, it's not completely public, but it's restricted, so it doesn't increase this education so much. But there we have a very detailed track of what's happening with these PERT cases that have been opened. We have a mailing list for these case managers and subject matter experts, and we have this public wiki that acts as a knowledge base that we use both internally and recommend other people to use as well. That's something you should probably take a look at if you haven't already. Okay, the future here is that the PERT process will continue beyond the GEANT 2 project, and there's this move to change the model slightly so that it becomes a federation of PERTs, so that national research organizations that already have PERTs or want to create these kind of national or local functions get better synchronized and have work better together. And the central PERT still continues to exist and coordinates these multi-domain cases and assists regions which don't have a PERT. And what has already been done, and there's a public report on these trade-offs of centralized and distributed PERT on the GEANT 2 web pages, and still being done is creating some kind of detailed policy for federated PERTs. And there's also going to be a workshop on how you would go about setting a local PERT. And this is expected to happen not so soon. So it's going to take a while to transition to this kind of model. At the earliest expected date is in August 2008. Okay, one topical challenge, general challenge I would like to mention here, because in this conference we have talked a lot about these light path networks, and there hasn't been so much experience debugging the problems with those networks yet, at least to my knowledge. And I would like to look a bit about what kind of tools the IP networks have. Usually there's ping and trace route and looking glasses, and if you have access to the measurement infrastructure, also different kinds of servers where you can check the bidirectional throughput and loss and jitter and that kind of things. It's also possible to use these remotely so that you don't need to have the access to the endpoints or even to the middle. It helps if you have access, of course, and it will be required at some point in the investigation if it doesn't go anywhere, but it's not required at the start. Okay, now if you compare that to lambdas, you usually have about 2 endpoints, and you have a number of networks in the middle, which may be transparent or they might not be. It depends on how those have been built. They might be might have some limitations on MTU. They might have some Ethernet switches in the middle, so on. So it might be possible to see some kind of traffic statistics in the middle, or it might not be possible. The networks in the middle usually have rather limited debugging capabilities, and I'm not sure how you would go about testing that kind of setup. Maybe you would need to connect a PC on the Lambda in the middle, or do something like that. And the most troubling thing, I guess, is that when there's a problem, you will the external people that would help, for example, PERT, would need the access to the either endpoint to debug because it doesn't go through any public infrastructure. Okay, the first thing, of course, is getting the Lambda to work at all. And I would like to ask the question, which kind of debug tools are available to the end user? How I see it myself, that the only thing that they can report basically is that, okay, pinging to some private address that's used on that Lambda doesn't work. And that's not very informative, but yeah, I would hope that there will be something better. And maybe there will be. And as for the operator of a specific part of the Lambda in the middle, maybe it goes through 5 different domains. One of those domains can basically say, okay, our optical power levels seem to be okay, so there's no cut. But that doesn't necessarily help. Depending on how it's built, the operator might also see some kind of SDH statistics or something like that, but that doesn't necessarily still help very much with the problem we're debugging. And what about the rest of the operators? They usually don't see what kind of statistics are available at the other parts of the Lambda. So they can only look at their own small piece and say that we seem to be okay, it must be somewhere else. So this is a bit troublesome, and we will probably need some better ways to look at problems with these kind of Lambdas as a whole. And now, if you manage to get the Lambda to work, it might be that there are some issues in getting it to perform to the satisfaction, as was mentioned in the earlier presentation. It might be that there's some minor packet loss somewhere, or well, usually packet loss is the primary thing. There could be some jitter and so on. And how do you narrow it down? It depends, again, how it's built, but in case there are no error statistics available, or those show 0, what you can do is you start replacing fibers, or start cleaning the fibers, or start replacing transponders, and work your way out. And if you have like 20 or 30 Lambdas, that's something that people seem to be think about as a future. That's not very scalable operation and management practice. So we will likely need something a bit more advanced in helping getting these to work okay. And it's worth considering how these are done differently in the IP routed network and Ethernet Lambda. And that's kind of trying to get people to think about how this kind of operations works with these Lambdas, and why it doesn't necessarily be scalable to have hundreds of Lambdas, especially if those are meant to be built dynamically or for a short while only. So it's going to be challenging to have this kind of infrastructure, but hopefully the tools will also develop on the side. Okay. Let's move to the PERT case. I was investigating we had this EVLBI traffic from Chile to the Netherlands. There's unfortunate date mismatch here. It's supposed to be September 2006, not 7. But there was a telescope in Chile that was best placed to observe this event, and that craft crashed on the moon, and the telescope recorded that, and the data was transferred to the Netherlands to JIVE, and the transfer used TCP. JIVE contacted PERT in advance, maybe almost 2 months in advance or 6 weeks, so there was, it could be said that they gave us plenty of warning to check connectivity, but we couldn't get good TCP performance on that link. Initially, it was between 2 and 7 megabits. And the characteristics of the paths were rather challenging, very long RTT, lots of different networks and operators that you had to go through. And in addition, in South America, there was significant bandwidth challenges. For example, one network's all uplink capacity was 90 megabits. So this was in no way simple case to look at compared to what kind of challenges usually we see in European tests. And here we see an illustration of the path. The child organization is on the top left corner. They had 100 megabit uplink, a couple of routers, a local university whose uplink was ATM 155 megabits. There was the local research network that had ATM backbone. The uplink is physically 1 gigabit, but only rate limited to 90 megabits. There was this South American international network, Red Clara, that had a couple of routers there. Those links were 155 megabits or a bit higher. That network was, in our tests, working quite good, so there were no issues there, even though it was a bit it had a slightly different capacity than some other networks in the world. And the link from South America was 622 megabits. That went through New York physically, so that increased latency quite a bit. And in Jean 2, there was a number of routers along the path as well, but our investigation showed that there were no issues that would relate to this case in the Jean 2 network. And also behind SurfNet there was this Jive that was the destination of these measurements. So what we can see here is that the path is really, really long, and it has significant impact on TCP congestion control, in the sense that especially if you would want to have a stable transfer rate, as the earlier speaker said, the recovery from a loss takes a long time. If you have a low delay, it will recover a lot faster. But in this case, if you would have a couple of packets lost with 300 millisecond latency, you would need a lot higher capacity to get it back to perform at some level. The target, as far as I understood, initially was 32 megabits per second, and that couldn't be achieved initially. And as we saw from that graph, the path was really long. There was this organizations at Chile and in Brazil, and Geant2 and SurfNet and Jive and so on. And the main problem here is that it's very difficult to establish contact with all of these different parties here to be able to make these kind of measurements that are needed. For example, run iPerf from certain networks to figure out where the bottleneck is and which network is causing packet loss, or which network has this issue with capacity. And we weren't able to establish any contact at all to the local university in Chile, and that's a bit unfortunate. But in the end, the other people in the path were really helpful, and we were able to get SSH access to some servers, so we could do some automated iPerf tests. And I think it's important to point out here that the expectations and the capacity might not always match. So especially coming from Europe, we might think that a gigabit is something that's kind of the minimum that we should be able to get. But in some parts of the world, the backbones aren't really that fast yet, and they don't necessarily have the funding to upgrade those. And we need to be careful on what we ask, or if we ask for that, whether we would be willing to also help with the with funding these kinds of upgrades, or at least provide these measurements, or do the traffic in such a manner that it doesn't disturb the other traffic. Usually these slower backbones are mostly congested almost all the time. And the thing here was that initially we saw something like 2 to 7 megabits performance, and the reason for that was that there were rate limiters at the borders of the university and the research network, 5 megabits, and that was a bit harsh. We had got an exception to that and got a bit better performance, but not so much. And there were also issues with how these rate limiters were configured. For example, between these national research networks, those had really small burst buffers, so if it got any higher, then it would cause some drops. And the improvements, we saw that when the limiter was removed and TCP settings adjusted, we got something like 15 megabits. And we did also do some periodic tests in October. We were able to get 20 to 35 megabits disk to disk, and lossless UDP could be achieved even at 70 megabits. But during the day, not so much. There was an upgrade in Chile which improved things a bit. The resolution for this case was something that was a bit unexpected, because the last top link between the last organization and the local university was that they upgraded the fiber and the path from 100 megabits to 1 gigabit, and the TCP performance jumped up significantly as a result, even though the UDP loss still persisted. And there was no will to continue resolving why this was the case, even though it shouldn't have helped. So we didn't really find the root cause, but we noticed that with this this change, the performance improved to a satisfactory level. Okay, I'll skip this because we are short on time, but we saw that when there was a limit during the weekend, performance was usually pretty stable here, but apparently there started to be some kind of cross traffic on Sunday because the performance jumped up and down in different measurements. Okay, let me check. This is the last slide. Okay, the funding, things to think about here is the funding model, which I already referred to. What does a site or national research network get funded for? Is there primary interest in provide network access and equal access to all the people that use their capacity, or provide higher capacity to some special groups? And this is mostly a value judgment that they will need to carry out. And in the networks that are bandwidth challenged, there are usually some rate limiters, and it's not necessarily even straightforward to find out where those are and how those have been configured. Okay, there are also some challenges about long RTTs, and the observation here is that the TCP buffer tuning only helps if there is no or very little packet loss. It might also make the things much worse if there is packet loss if you increase the buffers, because it will try to go very fast and then will drop down and never really recover, or in any case create this kind of up down behavior in TCP. So you will need to look at these kind of things as well. It might be possible to use something like DCCP, which includes TCP-friendly congestion control, but is otherwise UDP-like in networks where there's packet loss, or get the packet loss eliminated. And the one question that has been asked is that would it be possible to get some kind of light path, at least to some part of the path, and would that have solved the problem? I'm not sure whether there would have been available funding to provide that kind of light paths, and I'm not sure whether debugging that kind of light path performance could have been possible. And my observation here is that if you have these kind of bandwidth challenges networks which have less than gigabit Ethernet performance, it's probably better to spend the money on upgrading the network than creating separate infrastructure on the side. Okay, that's all I have here now. Maybe there's time for a couple of questions, if there are any.
Any question? Any question for Becca?
I just wanted to clarify one of your last comments. Were you saying that if funding is limited, it's better to over-engineer the capacity on the IP network, the NREN IP network, rather than provide light paths?
Yes, to a certain degree, because the way I think about this is that the IP, getting the IP equipment that performs up to, let's say, 1 gigabit, that's pretty cheap. But if you need to go to 10 gigabits or even more, that's going to be a lot more expensive. And for a certain amount of money, it might be cheapest to improve the IP network to, let's say, 1 gigabit or something like that. And if that isn't sufficient, then maybe look at some other solutions that might be more cost effective.
Does that work?
Yeah. Well, one of the things you were talking also about the complexity of debugging such a very long path, and it is more a remark than a question. I mean, you really did a lot of work to debug this whole thing, and it was interesting for us also to see how much work there was involved.
Mm-hmm.
But in fact, you said the results got better, but on the moment of the crash, we got back to 2 megabits per second. And I can't prove it, but I'm nearly sure that someone put the rate limiter on again. And there was nobody we could phone even, so, you know.
Yeah, I agree. And
the human aspect is pretty important in this kind of things.
Yes, I noticed that during the investigation, at one point we asked them to turn off some rate limiter. It was turned off, but it came back up a couple of weeks ago, after, and so on. And it was difficult to get contact to confirm whether it had been turned off, back on again, and so on. So it's when there are lots of organizations involved, it's very tricky. But it helps if there are these measurements points which we can look at without the kind of explicit cooperation with the local provider.
No more questions? Okay, so let's thanks again. Let me remember you that Terena needs your input for the preparation of the next TNC. So please let me kindly request you to fill the evaluation form. So we'll be very grateful if you do it. Thank you very much.